So can you guys hear me now and see the screen?
We can hear you now, but can't see the screen yet.
Okay. So hopefully you can see the screen now.
Yep, we can see the screen now.
Okay, thank you. Sorry about that. Some stuff was unplugged here in the room. Okay. All right. I'm going to go ahead and get started then. What we're going to do today is I'm going to review the answers to exam 3, and then we'll start on chapter 19, and we'll start that lecture. We'll finish up chapter 19 on Thursday, and then next Tuesday, so a week from today, we'll have a quiz, and that'll cover chapter 19. That's another thermodynamics chapter. Okay, so let's get started with the exam review. So the first question, a Bronsted-Lowry acid is defined as a substance that Bronsted-Lowry acids are proton donors. Number 2, molar concentration of hydronium ion in pure water at 25 degrees C is, that's 1 × 10⁻⁷. Remember, that's where that equilibrium constant from water comes from. Hydroxide times hydronium equals 10⁻⁴. Each of those are 10⁻⁷. Number 3, which one of these is the weakest acid? And you were given the Ka values. So remember, Ka values, equilibrium constants, that's products over reactants. So the hydrogen ion concentration will be in the numerator. So the smaller the Ka value, the weaker the acid. And in this case, the HCN is 4.9 × 10⁻⁻10. So that 10⁻⁻10th is the smallest concentration. So because that's the weakest concentration, it's the weakest acid. Number 4, an aqueous solution of a particular compound has pH of 7.46. What is the compound? The answer is a weak acid. Number 5, what is the pOH of an aqueous solution that contains 2.5 × 10⁻⁴ hydronium ion? So to solve this, what you would need to do is you would need to go ahead and you can calculate the pH, which is minus the log of the hydronium ion concentration. You get a value of 3.60. And then we remember that pH plus pOH equals 14. So by subtracting that 3.6, we would get our pOH value, which would be 10.4. In number 6, we have an aqueous solution that contains 0.390 molar HCl. And what is the pH of that? Well, HCl is a strong acid. So the hydrogen ion concentration and the HCl concentration will be the same. So you needed to do minus the log of the 0.390 value, and that will give you a pH of 0.41. In number 7, you're told that Hz is a weak acid. And then you prepare an aqueous solution of Hz by dissolving 0.02 moles of Hz in sufficient water to yield 1 liter of solution. You were also told that the pH of the solution was 4.93, and you wanted to calculate the acid dissociation constant. So what you could use is you could use that Henderson-Hasselbalch equation, pH equals pKa plus log, in this case, of Z minus concentration divided by Hz concentration. If we think of what the equilibrium expression in this is, it's Hz going to H plus Z minus. And so that what we see there is we can calculate the hydrogen ion concentration from the given pH. So remember, pH we were told is 4.93. So that means the hydrogen ion concentration is 10 to the minus 4.93. We go ahead and solve that, we get 1.17 times 10 to the minus 5th molar. We said that we wanted to get what Z minus is, and because of that dissociation reaction that we write, we see that we have 1 mole of Z minus for every mole of H plus. So that means that Z minus concentration is going to be the same as the hydrogen ion concentration. So we can go ahead and plug that into our Henderson-Hasselbalch equation. And so we have pH, which is 4.93, equals pKa plus the log of 1.17 times 10 to the minus 5 divided by that original concentration of 0.02 for Hz. Then it's a matter of going through and working through the math. And if you do that correctly, you get 6.9 times 10 to the minus 9 as the Ka value. Okay, number 8, the Ka for hypochlorous acid, HClO, is 3 times 10 to the minus 8. And then you're asked to find the pH of its aqueous solutions, that is 0.02 molar HClO. So once again, if you write that equilibrium expression, HClO going to H plus ClO minus, and we start with 0.02 moles, 0.02 molar HClO, 1 and 1 in terms of molar ratio for the hydrogen ion and the ClO minus. So we designate those as X. We write our equilibrium expression, Ka equals H plus times ClO minus divided by the HClO concentration. So we fill in our X's there. We have X times X in the numerator, in 0.02 molar in the denominator. It would be minus X, but we're going to neglect that X because we know it's a weak acid. We can tell that by the Ka value. And so we then solve for X, and that's 2.449 times 10 to the minus 5. But we're asked for pH, so then we need to do minus the log of that value, and you get a value of 4.61. Number 9, the acid dissociation constant for some unknown acid is 4.57 times 10 to the minus 3. What's the base dissociation constant for the unknown anion? So this is where we need to remember that Ka times Kb equals 1 times 10 to the minus 14. And so if we then plug in the Ka value we had and then solve for Kb, you should get 2.19 times 10 to the minus 12. Number 10, which solution has the highest concentration of hydroxide ions? So we're given pH values, a series of them. We remember that pH above 7 is basic. So those higher the pH number, the more hydroxide ion concentrations you're going to have, hydroxide ions you're going to have. And so that would, pH 12.5 is the highest one in this list. So that's the answer there. Number 11, hydrochloric acid is a strong acid. What does this mean? Well, strong acid means you get complete dissociation. So that's our standard definition for a strong acid. Number 12, which of the following expressions is the correct equilibrium constant expression for the following reaction? And the reaction was aqueous HF plus water. And water has that little L in parentheses, so that tells us it's a pure liquid. And remember, pure liquids don't show up in our equilibrium expressions. And then that goes to H3O plus F minus. And so if we remember it's products over reactants, we would then look at our coefficients. All the coefficients are 1. As I said, the water is a pure liquid based on that little L in parentheses next to it, so that one doesn't show up in it. So the correct expression is concentration of H3O plus times the concentration of F minus divided by the concentration of HF. Number 13, we're given a reaction and then we're told what the equilibrium constant is. It's 3.6 times 10 to the minus 3. And we're asked what does that mean? And so once again, products over reactants. So if it's less than 1, then we know that there's more reactants than there are products. And so the answer is reactants predominate. Number 14, which of the following could be added to a solution of acetic acid to prepare a buffer? And remember, when we talked about preparing buffers, we said there's 2 ways you can do it. One is to add the anion of that acid, and the other way is to add a strong base. So you dissociate out and neutralize some of the acid you started with. So the answer for this one is B, adding sodium acetate or sodium hydroxide. Number 15, you're given the acid dissociation constant of benzoic acid, that's 6.30 times 10 to the minus 5. And then you want to know the pH of a buffer prepared by combining 50 mils of 1 molar potassium benzoate and 50 mils of 1 molar benzoic acid. So you can use that Henderson-Hasselbalch equation again on this one. So you can take your Ka value, convert that to a pKa value, that's 4.2. And then you want to calculate the number of moles of the anion, the benzoate, and then the number of moles of the acid. And so you would do that by converting your milliliters to liters and then multiplying that by the molarity. In each case, the molarity was 1, so you get 0.05 moles of each of those. Then you would go back and plug those into the Henderson-Hasselbalch equation, and you get a value of 4.20. Number 16, pH of a solution prepared by mixing 50 mils of 0.125 molar KOH and 50 mils of 0.125 molar HCl is what? So what you want to do is you want to calculate how many moles of each of those you have. So once again, you would do that by taking your milliliters and converting that to liters, and then multiplying it by the molarity for each of these. So in this case, they both come out to 6.25 times 10 to the minus 3 moles of the acid, and the same for the base. So this is a neutralization reaction. So if you have the same moles of acid, same moles of base, it's a strong base, strong acid. So you neutralize the solution and the pH is 7. Number 17, the solubility of manganese hydroxide is 2.2 times 10 to the minus 5 molar. What's the KSP of it? So you would go ahead and write your equilibrium expression. So that's that the solid magnesium hydroxide solid dissolving into magnesium plus 2 moles of hydroxide. So you had to get that 2 moles in there. Then the KSP expression would be equal to the manganese plus 2 concentration times the hydroxide concentration, but the hydroxide concentration needs to be squared since there's 2 moles of that. You would go ahead and plug into the equation that solubility number. And so you'd have 2.2 times 10 to the minus 5 for the concentration of manganese plus 2. But because of our stoichiometry on the hydroxide, that concentration is 2 times 2.2 times 10 to the minus 5. And then that quantity gets squared. So the key to this one was remembering that because of that stoichiometry not being 1-to-1, you had to take into account the coefficient of 2 and how that affects things. So if you did all that, you get a value of 4.3 times 10 to the minus 14. Okay, number 18. Calculate the percent ionization of formic acid in a solution that is 0.322 molar formic acid and 0.178 in sodium formate. And then you're given the acid dissociation constant for formic acid. So once again, we can use that Henderson-Hasselbalch equation. We have a Ka, so we can calculate the pKa for that. We have concentrations of formate ion and formic acid, so we can plug those into our log term. And then we can go ahead and find the pH. Once we find the pH, then we can go and calculate out what the hydrogen ion concentration is. So if you did all that correctly, you got a 3.24 times 10 to the minus 4th molar for the hydrogen ion concentration. And then what you do to find the percent ionization, you ratio that concentration to the starting concentration of the formic acid. So you would have 3.24 times 10 to the minus 4th divided by 0.322. And then because we want it in percent, we have to multiply it by 100, and you get a value of 0.101%. So personally, I thought this was the hardest question on the exam. People did pretty well on it, so I was glad to see that. So congratulations on that. Because here you had to do a few things, and you had to remember how to do the percent ionization and all that stuff. Okay, so 19, a 50 ml sample of aqueous HCl solution is titrated with 0.375 molar in NaOH. The equivalence point is reached at 62.5 mils of the base. What's the concentration of HCl? So first thing you wanted to do was calculate how many moles of hydroxide you titrated in with that solution, 62.5 mils of base that you titrated in. So if you go ahead and calculate that out, so you take the mils, convert it to liters, and then multiply it times the molarity, that gives you the moles of base that were used in the titration. In this case, 0.0234 moles. If that's how many moles of base were used, then that has to be, because it's the equivalence point, this is a strong acid, strong base titration. That tells you how many moles of acid were there. And so if it's 0.023 moles of acid, you had 50 mil sample of it. So to calculate molarity, it's that moles of acid divided by the volume. And you have to express the volume in liters because it's molarity. So it's 0.0234 divided by 0.050, and you get a value of 0.69 molarity. So I thought 18 was the harder problem. I thought 19 would be pretty easy for you guys because you've done this in lab, and a lot more people miss 19 than 18. So that kind of surprised me. Number 20, the concentration of fluoride ions in a saturated solution of barium fluoride is what molarity? And then you're given the solubility product constant for BAF2 as 1.7 times 10 to the minus 6. So if you go ahead and write that expression, BAF2, the solid, going to BA plus 2 plus F minus. To balance it, you need a coefficient of 2 in front of the fluoride ion. And so then your KSP expression would be KSP equals barium plus 2 concentration times the fluoride concentration squared. So kind of similar to the earlier problem, then you can go ahead and see that you have, for every X of barium plus 2 that you get 2X of F minus. So if you substitute in for your concentrations X and then 2X for those, this gets you to where you have to find a cube root at some point. And this is where I'd mentioned, make sure you knew how to do that in your calculator. It looked like most people did, so that was great to see. And then you solve for X, 7.5 times 10 to the minus 3. But what you needed to remember that you want fluoride ion concentration, and fluoride, because of that 2 to 1 molar ratio, you had to go back and multiply this 7.5 times 10 to the minus 3 by 2. And then that would give you 0.015 molar, or 1.5 times 10 to the minus 2. So in general, I think people did well on the test, so that was nice to see. Any questions about anything on the exam? It is posted on Canvas if you want to take a look at it later or something. And if we don't have any further questions or any concerns about this, I'm going to move on to start chapter 19 and talk about that for a little bit. So let me pull this up. Okay, so chapter 19, we talked about some thermodynamics last semester, and we went through the first law of thermodynamics. So now what we're going to do in this chapter is go ahead and talk about the second and third laws of thermodynamics. So hopefully you remember what the first law of thermodynamics was. And that simply stated was energy cannot be created or destroyed, okay? So there's a certain amount of energy present. You can't make more, you can't destroy it. And so total energy remains constant. What you can do, however, is you can convert energy to different forms. You can transfer it from a system to the surroundings, or from the surroundings to the system. So basically, while you can't make or destroy energy, you can move it around and you can put it in different forms, okay? And that's what we said was the first law of thermodynamics. And so hopefully everybody, this rings a bell. And so remember when we talked about energy flow, heat flow, we used the term enthalpy, and that was the delta H thing, if you recall that. So, and we had all kinds of different enthalpies that we talked about, but what was in common about it is enthalpy really is heat flowing into or out of systems, things like that. we've also mentioned just a tiny bit entropy, and we're going to go into more detail on that today. Entropy is the measure of randomness in a system. So randomness, chaos, things like that, that's what you're talking about when you're talking about entropy. And these two things, enthalpy and entropy, so in other words, that heat flow and then the randomness in the system, those both determine whether a process is spontaneous. And so we're going to be more focused on chemical reactions and chemistry things, but really it's any process follows these rules. So we talk about processes that are spontaneous and ones that are not spontaneous. And so when we say something is a spontaneous process, what we say is that it occurs without any outside assistance. And so an example here on the right-hand side of this slide is you see someone's holding up 2 eggs and they let them go and they fall to the table and they break. So no one had to do anything other than let go of the eggs. So that's a spontaneous process. Now, if the eggs were to somehow come up off the table and go back up into the hand, you could stand there all day with your hand over those eggs and they're never coming up, right? Something would have to be introduced that would force those eggs to jump back up into your hand. That's not going to happen on its own, no matter how long you think about it or how long you have your hand there. And that's really what we're talking about when we talk about a spontaneous versus a non-spontaneous. And so it's exactly what it sounds like, something that happens without you doing anything to it. The thing about spontaneous processes is that they're only spontaneous in one direction. So like with the eggs here, we can let go of them and they'll fall, and that's spontaneous, but coming back up, that's not going to happen on its own. Someone has to do something for them to come back up. And so if the process is spontaneous in one direction, it's not going to be spontaneous in the reverse direction. A couple other things I want to mention is spontaneous reactions sometimes are fast, but they don't have to be fast. They can be slow as well. And so the speed of the reaction really has nothing to do with whether it's spontaneous or not. And the other thing is, don't confuse non-spontaneous with impossible. So the egg example is not a very good example to highlight this point, because once the eggs are broken, it'd be pretty hard to piece them back together and get them in the shell. But let's say that was a brick and you dropped a brick. The brick's going to fall and it's probably not going to break or anything. It's just going to sit there. But you could get that back up in your hand. You could somehow have energy to push it back up in there. So just because it's non-spontaneous doesn't mean it can't happen. It just means to make it happen, you have to do something to it. So there's some experimental factors that you can introduce that can take something and suddenly make it be spontaneous. And 2 things that affect spontaneity are temperature and pressure. And here we have an example of how temperature affects spontaneity. On the left-hand side, we have some water in an Erlenmeyer flask, and it's a little hard to see, but that's supposed to be frozen. It's supposed to be ice in there. On the right-hand side, we have the same water in an Erlenmeyer flask, and it's just liquid water there. So if we are, say, on the flask on the left, where we have ice, if our temperature is above 0 degrees C, because remember 0 degrees C is our freezing point, if that's above 0 degrees C, it's going to spontaneously melt, right? So just think of it, you put an ice cube out there, if it's not freezing out, it will melt. Same thing on the right-hand side here with the liquid water. If we're above 0 degrees C, nothing's going to happen. It's just going to sit there, right? But if we then drop it below the temperature below the freezing point, then it's spontaneously going to go and it's going to become a solid. It's going to freeze. So temperature and pressure, depending upon what it is, because we didn't change, in this case, the solution. They're both water, flasks of water. The thing we changed in this was temperature. And temperature impacted spontaneity there, depending upon which it is. So temperature, pressure can affect spontaneity is the takeaway there. We also can talk about reversible and irreversible processes. So a reversible process is simply where you have the system changes so that the system and surroundings can be returned to the original state by exactly reversing the process. This maximizes work done by a system on the surroundings. And so what that means is we can reverse it and get back to what it was. And the two examples we have up here, if we look at the diagrams at the top, we have a system in the middle and in the surroundings, and we add some heat to that system. And what you see is that surroundings will then absorb some of that heat from the system in order to get things back to equilibrium. A similar thing we see in the second example, where in this case, the system, its temperature has been lowered a little bit. And so what you have is a small amount of heat is transferred from the surroundings into that system. So in each of these cases, these are reversible because in one case, you increase the temperature of the system. The other case, you decrease the temperature of the system. And then what happened is the surroundings responded in a way that allowed you to get back to that initial state. And so you reestablished your equilibrium there. And that's what's happening, is where the overall system can change so that the system and surroundings get rebalanced, is how I think of it. And so that's a reversible process. So if we would have added that heat in, say on that first example, and if we then didn't have a way to balance that out, then it would be irreversible. But because in these cases, the surroundings was able to balance, those were able to balance things out, it's reversible, whatever that happened. Here's an example of an irreversible process. And so we define irreversible processes that they cannot be undone by exactly reversing the change to the system, or cannot have the process exactly followed in reverse. So in this case, let's take a look at this diagram. So what we have here on the left is we have this little container with a piston on the left-hand side. And in the middle, there's a partition that was put in here. Then on the right-hand side, the kind of the bluish, there's a gas introduced into there. And the left-hand side is a vacuum, okay? So there's nothing in there. So then in the next step, what is done is that partition is lifted up out of the container, and what do we see? We see that the gas that previously was just on the right-hand side of the container, it dissociates throughout the whole container. So that expansion of the gas occurs, and that's what we would expect based on what we've talked about in the past. And now we've got a uniform distribution of the gas done there. So the work done by the system is nothing. We didn't have to do anything to it to make it do that. It was a spontaneous process that wanted to happen, that happened. But now, if we wanted to get all of that gas back over to the right-hand side of things, we can wait there forever and it's never going to happen, right? We know that that gas isn't going to just magically all go back over to the right-hand side of the container like it's happened before. And so in order to get that back to how it was in the beginning, where we had all the gas on the right-hand side of the container, we would have to do some work. In other words, we would have to take that piston. Remember, we have this piston on the left. We would have to take that piston and start pushing it over. So in other words, pushing the gas over to the right, till we got it all over to the right-hand side of the container. Well, now we've got all that gas over on the right-hand side. Over on the left-hand side, there is none because we've used that piston to move it. And we're back to our original state. But to do that, we had to do work, right? We had to take that piston and move it and push on that gas and compress that gas. So to dissociate the gas, we didn't have to do anything. To get it back to normal in this case, we had to push on it. So this is an example of an irreversible process because it's not that you can't get back there, but to get back there, you had to do some work in this case. You had to do something. It didn't happen normally. Whereas we looked at these examples for the reversible process where we had a little bit of increase in heat or decrease in heat in the system. And then we saw the surroundings was able to just compensate for it without us doing anything. Here, we could wait forever, like I said, and this middle one is not going to look like the one on the right or the one on the left, no matter how long we wait. Unless we go and do some work, and in this case, compress that gas to get that. So does that make sense in terms of spontaneous versus non-spontaneous, and then reversible and irreversible processes? Okay. So the big thing I want you to take from here, there's two things we have here, is that because real processes can only approximate infinitesimal changes associated with reversible processes, all real processes are irreversible. But the real one I want you to remember is spontaneous processes are real processes. Because spontaneous processes are real processes, all spontaneous processes are irreversible. Okay, so if something is spontaneous, it's irreversible. Doesn't mean you can't reverse it if you do something, but it's not going to reverse on its own. And think back to that dropping of the eggs, okay? We drop those eggs, they hit, they sit there forever. We think about the gas example. We expand that gas. Unless we do something, it's going to sit there. It's not going to go back to how it was. Okay, so I'd like to talk about entropy a little bit more. Remember we said entropy is the chaos, is the randomness, is the disorder, those kind of things we think of. And so entropy is a state function. And remember, if we said something is a state function, it doesn't matter how you get there, it's just what'd you start with and what'd you end with, okay? So it doesn't matter if things take different paths to get there. It's like each of you, you started where you live and now you're in class. Doesn't matter how you got here, everyone probably took a different path, but the key is you started at home and now you're at class. So you would be a state function in that example. So because it doesn't depend on the path, we can write a delta S being equal to whatever the final value is minus the initial value. So it's just that change that we're interested in. We can find delta S by looking at the heat transfer from the surroundings at a given temperature. So remember here we have So we have delta S equals Q reverse divided by T. T is a constant temperature. And remember that small q is a heat term. And that's, we're saying that's the heat that would be transferred if the process were reversible. So for that constant, we're saying what would the heat transfer be if it was reversible? So once again, this is where the enthalpy stuff comes in. We're concerned about how heat flow impacts things. So this leads us to the second law of thermodynamics. Remember, we said the first law was energy isn't created or isn't destroyed. It's just moved around or changed forms or things like that. Second law of thermodynamics says the entropy of the universe increases in any spontaneous process. So for a reversible process, the delta S, the entropy of the universe, tells us that the entropy of the system plus the entropy of the surroundings equals 0. But for irreversible processes, and remember we said that spontaneous processes are irreversible. That was one of the things we talked about a few minutes ago. Then delta S of the universe equals delta S of the system plus delta S surroundings. And that's going to tell us that that's going to be greater than 0. Because remember, we're saying that the entropy of the universe increases in any spontaneous process. So think of it this way. If it's spontaneous, things get a little more chaotic, is what it's saying. Let's take a look at entropy on the molecular scale. So in a little bit, we're going to talk about thermodynamics and things like that. And that's looking at these kind of processes on a more macro scale. But before we do that, let's take a look at it on a molecular scale to try and understand it a little better. So on the left here, in the figure on the left, we have two molecules, one red one and one blue one. And they're in this kind of two gas balls here, one on the left, one on the right, and there's a stopcock in the middle. And so we have those two molecules, the red one and the blue one, on the left-hand side. And then we're going to see what happens, or what potentially can happen when we open the stopcock up and then allows them to go. Well, there's 4 different ways they can go. We can have it where there's a red one, or whether a blue one on the left and a red one on the right. We can have it where there's a red one on the left, a blue one on the right. We can have it like it started out, where there's a red and blue in the left, and then we can have a red and the blue on the right. Those are the only 4 combinations that we can have, okay? And so then, if we started with one red one, one blue one on the left, and then we opened it up, what are the odds that we have that we have them, the two on the left, one blue, one red on the left, like we started out? Well, you can actually do that calculation. If you have 2 places the molecules can be, okay, they can either be left or right side of this. And then the power is the number of molecules. And there's 2 of those. So simply, it's 1/2 squared. That's the odds of those 2 molecules being in that one on the left, like you started out. Okay, so pretty simple calculation, pretty easy to understand. But you don't often have just 2 molecules, okay? Think of that as, remember Avogadro's number? Remember we said Avogadro's number number of molecules in a mole, that was 6.02 times 10 to the 23rd. So if we had 1 mole of gas, okay, and we did this same experiment, now to figure out what it would still be 1/2 because we have the 2 sides of the apparatus. But now, instead of it being raised to the 2nd power, it would be raised to 6.02 times 10 to the 23rd, because that's the number of molecules that are in a mole, right? So I certainly didn't bother to calculate that out, but I know it's a really tiny number. And really, essentially, it's 0. So what this is saying is that you essentially have 0 chance of it all winding up in that left-hand side. Okay, and this is where this stuff gets really complicated. And this is where there's a guy named Boltzmann, and we'll talk about some Boltzmann stuff here in a moment. This is where he came out and did a bunch of math to figure out some of this stuff and explain some of this. Because it's pretty easy to see when you just have 2 molecules. But reality is, you're usually not too concerned about just 2 molecules. Okay. So let's talk a little bit more about entropy on the molecular scale. So we know that gases expand spontaneously and they fill up whatever volume you give them. Remember back when we talked about gases, that was one of the things about gases. You put them in a little container, they fill the whole container up. You put them in a big container, they fill the whole container up. That's what they do. And so if we look at another one of these examples, in this case, we have gas in the enclosure on the left, and on the right side, that part of it has a vacuum, so there's nothing there. With our stopcock again in the middle, we open that up, and what happens is the gas is going to diffuse over to the B side of our apparatus. Because remember, we said gases like to expand to fill whatever is available to them. And so what this will happen now is we started with 1 atmosphere up here on the left. It's diffused over, and now that pressure has decreased to 1/2 atmosphere on each side. We're assuming all these are the same size and stuff like that. That's a spontaneous process, okay? That happens without us doing anything to it. All we had to do was just open it up, and there goes the gas. Now, if we want to get the gas all back to the left-hand side, the A side, we can wait for a long time, and that's never going to happen, okay? And so in order to get that to go back to the other side, we would have to do some type of work or do something to it. Kind of like if we think back to our piston example, if we put some pressure on it, we could push it all back. But it's not going to be spontaneous. So that reverse process is not spontaneous. And so the most probable arrangement, based on how we know gases like to behave and the spontaneity of it, is that we have equal amounts on the 2 sides. As I said, this is great to look at these individual molecules, these what I call small amounts of things to see what they do. But that really isn't what you're usually concerned with. You're usually concerned with bigger systems and bigger processes and things like that. So thermodynamics is the study of these bulk properties of substances. And the problem is that we've been talking about things on a molecular scale. How do we translate something happening on a molecular scale to something happening on a bigger, broader scale? And that's where we use statistics. And by statistics, what they're always, in this case, talking about is probability, okay? The funny thing about thermodynamics is you never, at least to me, you never get a real straight answer. It's always the probability of something happening and things like that. And you may remember last semester, I think it was towards the end of the semester, we did a lab where we started doing some computer simulations to see where electrons were and all that. And it was like the probability of it being here. And if it was more probable, it'd be a little darker, less probable, a little lighter on the computer screen. Kind of the same thing with this. This is all statistics. It's all probability of predicting what's going on. And so statistical thermodynamics, if you stay in chemistry and take physical chemistry, you'll get to learn more about this in detail. A lot of math involved. We won't do that in this class. We're just talking about the theories behind it. And another term I'd like to introduce is microstate. And so a microstate is just a single possible arrangement of position and kinetic energy of molecules. And in a moment, we'll have some further information, some pictures that'll explain that a little bit better. Okay, so Boltzmann used these microstates, okay? And there are a lot of microstates, and you'll see why that is in a few moments. And so he came up with a term W to represent the number of microstates. And entropy, remember our randomness, is simply the measure of how many microstates are associated with a particular macroscopic state, okay? So you see some macroscopic state, something that happened, that's composed of all these little tiny microstates added up to give you that one big event. So he came up with this expression to link the number of microstates to the entropy of the system. And so entropy equals K, which is the Boltzmann constant, is 1.38 times 10 to the minus 23rd joules per Kelvin. Natural log of W, and remember we said W is that number of microstates. So really what we're saying in entropy is that it's a measure of how many microstates are associated with a particular macroscopic state. We said earlier, entropy is a state function. So final minus initial gives you the overall change. We're not concerned about the path to get there. It's just the final minus initial. And an increase in the number of microstates increases in positive entropy. In other words, it gives us more disorder, okay? And so once again, entropy increases with the number of microstates of the system. And here we have our expression. We can rewrite that delta S. Okay, so here's a rewriting for delta S, for S final and then S initial. So we have that Boltzmann constant times the natural log of the number of microstates for the final minus that same thing for the initial. We can rearrange those and have K times the natural log of final divided by initial for those microstates and get a value for delta S there, an expression for delta S rather. Let's talk a little bit about some things that impact the system. So we talked a little bit about temperature already. So let's talk about volume for a moment. So if we increase the volume, there's more possible places for the molecules, right? If there's more possible places, then that means there's more microstates. We said if you increase the number of microstates, then you increase the entropy. So, and here, think about gases, okay? We'll talk about some other liquids and solids, but for right now, let's think about gases. So you increase the volume, increases more places for the molecules to be, that's more microstates. More microstates means increased entropy. If we increase the temperature, what happens to those gas molecules if you increase the temperature? They start moving around more, right? We've said that before. You have a gas, you heat it up, the molecules move a little more quickly. So that means we've increased the average kinetic energy. If we've got a greater distribution of molecular speeds, then there's more possible kinetic energy values, resulting in more microstates, resulting in more increased entropy. So the takeaway from these two: increase the volume, increase the temperature, increase the entropy. And that makes sense, right? You have these gases, you increase temperature, you increase volume, you get things jumbled a little bit more, we get a little more chaos. We said that's what entropy is. There's another type of microstate that we are concerned about, especially in chemistry, and that's molecular motions. And molecular motions are pretty neat. This is like I said, the other stuff is okay, but this really gets down to more chemistry and bonding and things like that. So let's talk about this for a little bit. So there's three types of motion we're going to talk about with regards to these molecules. The first is translational, and that's the movement of the entire molecule from one place or another. So that's where we were talking about the gases, and you heat them up or you increase the volume, and those gas molecules, the whole molecule moves around. That would be translational motion. But there's also two that I think are a little more interesting. One is vibrational and one is rotational. And so vibrational is defined as periodic motion of atoms within a molecule. And to understand that, let's look at the figures down on the bottom here. So the first three on the left is marked with vibrations. So you see these atoms. So we've got a red one and then two white ones there. And you see some double-sided arrows there. What I would ask you to do is think of those bonds as springs. Okay, and think of if this bond on the first one was a spring between the red atom and the white one, what would happen if that was a spring and you started playing with it? It would kind of go back and forth, wouldn't it? So that's a vibration that can occur. It can occur between the red and the white one on the right, the red and the white one on the left. You can have those motions going. That's what molecules do. And you see other examples of this. The second one we see is a vibration where these two white ones are kind of going out and in, out and in. The third one, we see where the one on the left is going, you see that how the arrows are drawn going out. The one on the right, the arrows are drawing so that they're going in. All of these kind of vibrations that you see there are going on in molecules. And that's the vibrational stuff that we're talking about here, the motion. These vibrations occur at frequencies that are known. And there's a whole part of analytical chemistry called spectroscopy, where people study these and use these vibrations by knowing what wave number or wavelength they occur at or what frequency to do analysis of compounds and identify them. So these are pretty characteristic of different kinds of bonds and things like that. But the point for us here with this second law of thermodynamics that we're talking about is what that means is those are all additional microstates. And this gets why I was saying before, it gets really, really difficult and really complicated to figure all this out, which is why the thermodynamics was developed. The other one is rotational. And so rotation of the molecule, think of it there, you have an axis and it spins around it. And the example we have on the right-hand side here is, think of it as an axis coming down from the top through that red atom. And then just kind of like with those little whirligig things, you're spinning it around. Okay, so it's rotating around on that axis. So look at this, we've got the spinning, we've got these different vibrations around the bonds, we've got all this stuff going on. Now, here we have three atoms. Think of if you have molecules that are bigger molecules and you have even more atoms. All this stuff's going on, right? All those bonds have stuff going on. You have rotation. And that's not even counting the translational that we talked about up front. And so what you see is that you quickly add up to a lot of microstates. And as you get more atoms and more complex molecules, that adds to it even more. So the point to this, I think the easiest takeaway is there's a lot going on here. There's a lot going on with these molecules. So just remember, as you increase the number of microstates, then you increase the entropy. We said that the temperature increases it, the volume increases it, the number of independently moving molecules increases it. All that hopefully makes sense. Think back to when we were talking about solids and crystal structures and all that kind of stuff. This is a few weeks ago. It's been a while now. But think back to that. And what did we say? We said that in terms of movement, there's the most movement in gas, then liquid, then solids, right? So if we think of entropy being that chaos, the more locked down something is, the less entropy, the less chaos there is. So just as we said that movement was greatest in gases, then liquids, then solids, that track is the same way that the entropy tracks as well. Entropy is greatest in gases, then liquids, then solids. The randomness is less in solids than in gases and liquids. If we have a system, if we have gases that form from either solids or liquids, we're going to increase the entropy, right? We're going from more ordered systems to less ordered. If liquids or solids, or liquids form solids, we're going to have less randomness. And also, if the number of gas molecules increase, then the entropy increases. Let's take a look at what we're talking about there. So in the top figure, we're saying that entropy increases as water goes from a solid to a liquid to a gas. And so on the left-hand side here, we have our frozen water, our ice, and so those molecules are pretty stationary. They're in that solid crystal. The molecules themselves really don't move. We still have the molecular vibrations. Okay, so that was the kind of, remember the bonds and the spring and that kind of movement. But that's it. So that means we have fewer microstates. Then we get into liquid, okay? But we still have the vibrations as we had in the solid. But now we start to get some other movement. We can have that rotational movement. We're not getting a ton of movement around in the solution, right? But we have more movement than we had in the ice. Now we get to the water in the gas phase, and now we have a lot of microstates because we've got all the ones that we had previously, and now the molecules can move around pretty easily because they got a lot of space. So that is kind of a visual of how that entropy increases as water goes from solid to liquid to gas. Down at the bottom here, we have a reaction that occurs. So on the left-hand side, we have 2 moles of NO plus 1 mole of O2, and that yields 2 moles of NO2. So what we see is that the entropy actually decreases here. And why is that? Well, on the left-hand side, we have 2 moles plus 1 mole, so 3 moles total of gas. Now on the right, we form 2 moles of NO2. So we have fewer moles of gas molecules. So 3 moles of gas molecules on the left, 2 on the right. So we have these gas molecules, and in this case, the molecules are moving around pretty much the same. You're having the same type of processes occurring within the molecule. But now, because our reaction resulted in a decrease in the number of gas molecules, in this case, the number of microstates decreases, and then the entropy decreases. Okay. So the next thing is that we're going to talk about is third law of thermodynamics. I don't want to start that today because we won't get through it. So we will pick up with this on Thursday. Just to remind you again that next Tuesday, we will have a quiz on this chapter. So we'll finish this chapter up on Thursday. Next Tuesday, have a quiz, and then kind of go from there. Any questions about anything before we end? Okay, thank you.